Good afternoon, ladies and gentlemen. I'm Pei Dongyang from University of California, Berkeley. I'm very honored to join with Professor Tianjun Zhou, professor at the University of Chinese Academy of Science, to co-chair this afternoon's section. This section is about science leads climate transformation, building a climate-resilient future. It consists of two parts. First, we will have 6 keynote speakers who will present their speech for around 15 minutes each. Then we will have an exciting panel discussion afterwards. I'm very excited to have all these fabulous speakers lined up here. It's going to be a great opportunity of learning cutting-edge insights on scientific and technology strategies, as well as action guidelines to address climate change and achieve sustainable development. So there will also be a discussion on how to lead climate transformation and low-carbon transition from 3 directions: climate policy, green low-carbon technology, and international climate cooperation. Through these discussions, this forum aims to provide reference and guidelines to promote resilient global climate development and accelerate carbon neutrality. Let me first briefly introduce today's keynote speaker, Professor Richard Zare, Stanford University. Professor Richard, no, stay there, stay. Professor Paul Chiric, Princeton University. Professor Graham Farquhar, the Australian National University. Professor Gang Chen, MIT. Professor Chenghong Zhang, Peking University. Professor Huan Liu, Tsinghua University. Now let me officially introduce our first keynote speaker, Professor Richard Zare from Stanford University. He was awarded 2005 Wolf Prize in Chemistry, and he is the Margaret Brake Wilbur Professor in Natural Science and the Professor of Chemistry at Stanford University. The title of his speech is Using Water Microdroplets for Achieving Sustainable Living. Let's welcome.
Thank you. What a pleasure to be here. Let me point out to everyone, well, that's not much of a laser pointer at all. Let's try this one. Yes. Please, if you want a copy of this talk, just email me and I'll send you a copy, so you don't need to take any notes. Let's begin and give you some background facts. Bulk water is relatively inert. It's benign. Swim in it, need it for life, right? And it's great for dissolving polar compounds. Water droplets, I'm going to try to convince you, are highly reactive, can cause marked acceleration of the rates on chemical reactions occurring in them, and can even cause new reactions to occur that do not take place in bulk water. Okay, let's look at this. And now, the question will be, why? Why is the difference? What's going on? And I need to explain to you some of the differences between bulk water and water microdroplets. No 3-dimensional hydrogen bonding at the surface of a microdroplet, can't. Evaporation is going to go on. That can concentrate things. You have gas-liquid interactions. Gases can come in, not in bulk water, but at the surface. There's going to be a huge electric field. Now, people have really, Zhonglin Wang has really taught us about contact electrification, as well as some other people. You put two phases together that are different, you have electrons that can go and jump between the phases. You get charging that goes on. You don't even need to rub them. And you get an accumulation of solutes at the hydrophobic-hydrophilic interface. The electric field is so strong it can align reagents, makes it viscous, and really changes its properties, very much of the water that you have there. Again, will affect reactivity, affects the entropy term. Entropy term, remember, is related to delta G equals delta H minus T delta S, okay, and very important. And we get all these other constants changing. Let's go on. So let's ask the question, what do you find in a 1 liter beaker of water? Well, everybody says the answer is simple. It's going to be 55 moles of H2O, HOH, and there's Avogadro's number, something like 6 times 10 to the 23. So there's lots of water molecules. And you ask, what else? Well, there is something else, not much. 10 to the minus 7 moles of H+, we call those the hydronium ion, and 10 to the minus 7 moles of OH-. That's the hydroxide ion. And that's why everybody who begins chemistry learns that the pH, which is the negative logarithm to the base 10 of the H+ concentration for neutral water, room temperature, 1 atmosphere pressure, is 7, as I'm telling you, okay? But now ask someone, what do you think the pH is of a water droplet in air? And because you're a professor of chemistry, they're going to pause, because the answer is probably not 7 when you start to ask that question. And indeed, you're going to start to see some very strange things happen. We're going to find that the water droplet surface is really loaded up with ions, electric field, and radicals, which we're going to get to. Let me show you that. This is the key to what's going on. In bulk water, I'm using a B for bulk water, okay? H+ and OH- do not go on to make .OH and .H. This electron transfer process is endothermic by this amount as calculated by DFT calculations, okay? Yeah, it doesn't happen. If it happened, you'd have hydrogen gas bubbling from inside water. No one's seen that, okay? But now, this is what's exciting. In liquid water at the air-water interface, okay, this is the surface. This is now exothermic. It happens. You have electron transfer, helped very much by that electric field. And now we have H dot, that's the hydrogen atom, and OH dot, that's called the hydroxyl radical, which some of you know from atmospheric chemistry is what cleans things up. They're very reactive. That's going to go on to do all types of chemistry. And that's what I'm going to be telling you about. And it's going to be related very much to another topic. And I want to just show you this so that you believe me, because you might not at all in the beginning. This is a compound which can capture radicals. It has a name, forget it, other than DMPO. And I'm showing you in a nitrogen environment, when you spray water droplets, Yusha in my group has found that you get both OH dot and H dot. Okay, and you don't see, of course, in pure nitrogen, you don't see any O2-, but now add air, the O2 comes in and makes O2-, so we see it, okay? And this is interesting. Full of radicals, suddenly that are there. That's called the superoxide radical anion. We'll go on. So let's now talk about something called nitrogen fixation. What is nitrogen fixation? It refers to any natural or industrial process that causes free nitrogen, N2, which is a relatively inert gas with a triple bond, plentiful in air, to combine chemically with other elements to form more reactive nitrogen compounds, such as urea, nitrates, nitrites, all absorbed by plants. We need them very much. Why do we need them? Why do plants require nitrogen? Just to remind you, so we're all together with this. It's a key component of amino acids. okay? Proteins and enzymes get formed from them. It's an important part of chlorophyll. Think of the structure of chlorophyll. It has nitrogen in it, right? And that's necessary for photosynthesis, makes plants green. Nitrogen is also a key component of genetic material, like DNA. And so it's very important we get nitrogen, okay? Microbes do that at the roots of plants, but now fertilizers make it better. So most common nitrogen fertilizers are ammonia, ammonium nitrate, and urea. Let's turn to the production of ammonia. That's done by taking N2 and 3H2 to make 2 NH3s. Okay, that's ammonia. Where does the H2 come from? It comes from natural gas, methane, which is treated with steam, producing lots of CO2 and hydrogen. Okay? Here's how you make the nitrate. Once you have ammonia, you can nitrate it with nitric acid. Here's how you make urea. Same idea, okay, of combining it. The famous Haber-Bosch process runs under high pressure and high temperature, as shown here, sufficient to break the nitrogen triple bond. And this, I told you what the source of the hydrogen is. It's methane. Again, hard work, a lot of energy involved in doing that, breaking CH4 apart. And subsequently, the carbon monoxide with a nickel catalyst gets turned into more carbon dioxide. And so what do you find out from this? Ammonia accounts for more than 2% of the global energy consumption in the world and 1% of the carbon dioxide that we breathe in and out. Okay, that's a lot. So if we want to get away from, again, a difference in our making things towards carbon zero, if we could find a better way to make fertilizer, it would really matter. And that's stimulating people. Can we really use water as a source of hydrogen in place of methane, like natural gas? Okay, I'll show you how. Here we do. Water, we just are pushing it out and spraying it with nitrogen, gas. It's like a perfume bottle. Squeeze it and you get droplets. I let these droplets go onto a mesh. This mesh contains a catalyst that holds the nitrogen in place. What is it? It's called magnetite, an iron oxide. And it's helped by having a little bit of Naphion to actually add H atoms to this process. Here's the distance we travel. Okay, and what do we see with the mass spectrometer? We see such things as hydrazine being formed, and we see ammonia being formed. All being done, please, room temperature. No light is being used to do this. You do it in the dark, do it in the light. No electricity is being applied, which is not a voltage. This is not electrochemistry in the traditional sense, but it is electrochemistry. It's electrochemistry at the interface of water droplets. And I'm showing you some more results with compressed air. You don't need pure nitrogen because air is mostly nitrogen. About 4/5 of air is nitrogen. And what else? Here's without, compressed nitrogen without the catalyst. And you get other stuff. It's the OH again. Here's the amount of the ammonia yield. It's achieved at room temperature and so on. And it remains to be determined whether this process can be successfully brought to an industrial scale in a commercially viable manner. If it could, I believe it would change the world. Okay, what's possible? But there's ways to go. Meanwhile, we have very new chemistry happening. Chemistry made possible at the interface with water droplets. And lots more can be done this way. And here it goes through a mechanism. I'm not sure, I have about 5 minutes left, so I can mention a little bit to you about this. People are always worried. They say, where did the energy come from? And I want to tell you briefly where it's coming from. You're breaking hydrogen bonding when you make water droplets at the interface. You're using up that, you have to put that energy in, and you get it back out as chemical energy. And that's what's going on in part. And I'm actually going to go through the various stages as you show here. And here's a whole map of it as to how it happens with the reaction coordinate. And I can go through all these steps that's involved, okay? Let's not. You get a sense of what's happening. You either want to study this in more detail leisurely, but not now is the time. Not enough time in this talk. to go through all the steps of having this thing come off, and it does, okay? Some steps are uphill, but we have electric field to help us. So here are some related achievements. If instead you don't use nitrogen, but you use carbon dioxide with nitrogen, you can put the carbon dioxide in the water, that's called soda water, or you can have it alone as a gas. You now get, believe it or not, urea. One step, room temperature, same way. Very, what we call green chemistry, very eco-friendly. And what other step? We can turn water, with water droplets, we can turn the CH4 into methanol and other oxygenated methane-type compounds. This is important because, as I mentioned about 2 days ago at another talk at this meeting, methane as a greenhouse gas is 80 times more powerful than carbon dioxide, and therefore about 25% of the warming is right now coming from the 2 parts per million of methane that's in the atmosphere. If we learn how to remove it and degrade it, we win. Even if we turned it into just carbon dioxide, we win. Okay? We're not. We can do something more useful. So with this, I think I'm going to stop and try to have you understand many things can be done with water microdroplets, many possibilities, and give you a sense of why it is I love water microdroplets. Thank you all.
Thank you, Professor Zia, for that amazing chemistry. Now I'm privileged to introduce the second speaker, Professor Tianjun Zhou, who is the Deputy Director General and a professor at the Institute of Atomic Physics of Chinese Academy of Science. He is also an accomplished professor at the University of Chinese Academy of Science. And his speech will be climate warming and extreme events. Let's welcome.
Good afternoon, ladies and gentlemen. My background is climate modeling, so today I will talk about global warming and also the associated extremes. Hope everybody still remember the just passed hot summer. The world has just experienced the hottest summer on record. What I show here is the surface air temperature anomalies of the world and also the evolution. You can find the UN Secretary General stated that the hot days of summer are not just barking, they are biting. Climate breakdown has begun. Climate is evolving faster than we can cope with, such as extremes. There are many pictures from the media, and here is Rome or Italy on August 23rd. You can find people were cooling off near the Piscine. For most people come from North America, I hope you still remember the heat wave occurred on the June 30. You can find the outdoor surface air temperature is above 46 degrees Celsius. This kind of heat wave was caused by atmospheric circulations named as heat dome. So, after seeing all these pictures, I believe you will ask one question. Why did all these events happen? The answer has been given by the assessment report of the Intergovernmental Panel on Climate Change. It's called IPCC. It says the recent changes in the climate are widespread, rapid, and intensifying, and also unprecedented in thousands of years. And here is the global mean surface air temperature in the observation. You can find in the past more than 100 years, global warming is evident over the instrumental period. If we focus on this time period, 2011 up to 2020, it's already 1.1 degree warmer than the pre-industry era. If we extend the time series back to the past 1,000 of years, you can find the past century warming actually is unprecedented in more than 2,000 years. If we compare the warming speed, what I show here is the warming rate in the early decades and also in the recent decades. You can find the warming has accelerated after the 1970s. In other words, the warming is getting faster and faster. How about China? And here is the annual mean surface air temperature averaged over continental China. You can find the warming trend is consistent with global average. More important, in recent decades, you can find the warming rate is also increasing. The global warming is not purely evident in surface temperature. We can also find signals in other components such as the cryosphere, biosphere, and ocean. There are evidence from the concentrations of CO2, the changes of precipitation, the changes of glacier mass loss, the global surface temperature, the global sea level, and also the ocean heat content. So the changes are occurring throughout the whole climate system. After seeing all this evidence, the second question you might ask is, are the observed changes natural or human-made? We also give our answer in the IPCC report. It says, it's indisputable that human activities are causing climate change, making extreme climate events, including heat waves, heavy rainfall, and droughts, more frequent and severe. These kinds of conclusions are supported by climate modeling and also detection and attribution. What is climate model? Climate model actually is a digital twin built on the supercomputer. It can help us to understand the reason of the past climate change and also project the future change. And here is a photo from Professor Manabe of Princeton. He is a 2021 Nobel laureate. He is regarded as the father of the climate models. Based on climate models, we can understand the past change. What I show here is the surface air temperature in the observation as shown by the black. In the supercomputer, by using climate models, we can specify the human and the natural forcing and also natural forcing only. You can find, if we specify the anthropogenic forcing, we can reproduce the observed warming trend. So human influence has warmed the climate. The observed climate change is not purely due to human activity. There are also contributions from natural factors such as solar variability and volcanoes. How to detect the observed change? In this regard, we need the technique of fingerprint detection. And this is the contribution of Nobel Prize laureate Klaus Hasselmann. He is the pioneer of the so-called optimal fingerprint detection. Based on the detection method and also climate modeling, we can estimate the contribution of human activity to the observed changes. For example, here is the change in observation, and here is the change the contribution of greenhouse gases, and here is the contribution of aerosol. You can find the observed warming is driven by emissions from human activities, with greenhouse gases warming partly masked by the aerosol forcing, by the air pollutants. We can also detect the contribution of human activity to extremes. And here is the result for hot extremes. Warm color means the heat waves are increasing in the observation. You can find over most part of the world, including Asia, the heat waves are increasing and also can be attributed to the human activity. We can do similar analysis to the heavy precipitation. Again, you can find in many parts of the world, we can find increase of extreme rainfall, and also we can detect the anthropogenic forcing. So, after seeing all this, the third question you might ask is, what will our climate look like in the future? To answer this question, first, based on the IPCC assessment, The conclusion is the changes we experience will increase with future warming. This conclusion is based on the projection. To project future climate, we need to develop the so-called scenarios. For example, in the coming century, we can either emit CO2 in this way, or this way, or this way, or in this so-called low and very low scenarios. We can use this kind of emissions of greenhouse gases to drive climate models and then check the response. The answers are given here. You can find we have choice. We can either live in a world with only 1.5 degree warming. If we follow the very low emission, that means we achieve carbon neutrality in the year 2060. We can also live in a world under 2 degree warming. However, if we do nothing, the future world will be 4 degree or even higher. There are also changes to the extremes. And here, I show the examples, the so-called once in 10 year heat extremes. And the global warming of 1.5 degree, the frequency will occur 4 times, and also the intensity will increase about 2 degrees. Under 4 degrees of global warming, you can find the frequency will increase to about 9 times, and also the intensity will be 5 degrees stronger. If we examine the so-called 110 year extreme rainfall, you can find a similar conclusion. So, associate different elements of the global warming, both the frequency and the intensity of extremes will increase. How about the mean sea level change? And here I show one example for the year 2300. This is under very high emission scenario. That means we do not reach carbon neutrality and continue to emission greenhouse gases. You can find the global mean sea level will increase about 7 meters. Please note the altitude of Shanghai is only 4.5 meters. You can imagine that kind of situation, a global increase of sea level pressure with about 7 meters. So, after seeing all these evidence from observations, detection and attributions, and the projections, the last question you might ask is, what's the implication of all this information? And here, I show the climate of current and future generations. For people who was born in 1950s, you're already 70 years old and already live in a world which is about 1.1 degree warmer than the pre-industry area. But for our children who were born in 2020, in 2019, they will be in their 70 years old. They have a choice. They can either live in a world warmer than 2, 3, or 4 degrees. They can also choose to live in a world with warmer less than either 2 degrees or 1.5 degrees, as the Paris Agreement declared. So, the final stage for this talk is to limit global warming. Strong, rapid, and sustained reduction in greenhouse gases are necessary. That's all for my talk. Thank you.
Thank you, Professor Zhou, for sharing the great insight on the extreme events. Our next speaker is Professor Paul Chiric, the recipient of the 2019 Ernie Award in Advanced Environmental Solutions. He is also the Edward Sanford Professor in the Frick Laboratory, Princeton University. Due to some reasons, he cannot join us today, but he has sent his video. So let's watch the video together. The talk's title is Reimagining the Periodic Table. Sustainability Challenges Arise from Elemental Scarcity.
I'd like to thank the organizers for the opportunity to speak today. What I'm going to tell you about is a different view of carbon footprint and how you interact with it through the periodic table. I'd like to begin by asking you a question. And that question is, How many elements do you think you will interact with on the periodic table today? Most people think it's 20 to 30. In fact, it turns out it's 75 to 80. Now, when thinking about the answer to that question, I'd like to ask another, and that is perhaps a bit easier to answer, and that is, are all 80 of these elements abundant on Earth? And I think we will all agree the answer to that is clearly no. So what that means is your day-to-day life is inherently unsustainable. And so the question is, where does it come from, and how do we improve upon it? You carry a periodic table with you almost every day, and that's your mobile phone. There's anywhere to 30 to 50 elements in that phone, and I'll return in a moment to figuring out which ones are there. My expertise is the area of catalysis, and as I'll show you, catalysis is used often with a reliance on exotic elements like rhodium and palladium to make the medicines that we need for our quality of life. And finally, even household items like your cooking utensils have an elemental footprint that relies on precious metals like platinum. So let's return to your mobile phone for a moment. There was an experiment done a few years ago in the United Kingdom to try to discern how many elements are actually in your mobile phone. And it turns out, as you can see on the slide, that it takes around 100 kilograms of carbon dioxide to produce the iPhone 14. To try to discover how many elements were actually in the phone, what was done is the phone was ground up in a blender and then analyzed using chemical techniques. And what the chemists found was that, not surprisingly, the battery had lithium, cobalt, carbon, and aluminum in it. The screen had a bit more exotic elements like the rare earths and the lanthanides. And not surprisingly, the electronics were rich with a variety of elements from across the periodic table. So how this deals with sustainability is that if these elements are rare on Earth, we go to far-off locations, dig deep into the ground, emit a lot of carbon dioxide to obtain these elements, put little bits of them into mobile phones, and then disperse them again not to be recovered. That itself is inherently unsustainable. And so as we think about net zero, this too has an elemental consequence. And so we've defined as scientists energy transition materials. What that means is, and I'll show you in more detail in a moment, we're going to have to increase our mining in precious metals like silver and rare earths, and especially indium. The green ambitions of the Netherlands alone will consume almost all the supplies of these global materials if we keep on the current trajectory that we're on. If we look, for example, at wind turbines, these too have an unsustainable elemental footprint. There's up to 500 kilograms of neodymium in the magnets to make the blade spin. There's 45 tons of non-recyclable plastic, and there's 2,500 tons of concrete to support the structure. As you might know, concrete manufacturing is one of the largest emitters of carbon dioxide on the planet. One other question you might ask is, where do all these components go once the windmill is at its end of life? The same is true for solar panels. So we have to purify and obtain silicon, which has a carbon footprint, and much like your mobile phone or the wind turbine, there's quite a few heavy metals that are often unrecovered in the use of a solar panel. I find this quite interesting that the amount of solar panel waste by 2050 is going to be equal to 60 million cars. So this is quite an effort and something we need to think about as we talk about cradle-to-grave analysis as we move to a wider adoption of alternative energy. So as I said in the beginning, my expertise is in the area of catalysis, and I want to show you a couple of vignettes on how catalysis, often cited and is a key driver of sustainable chemistry, also can be improved. So everyone listening to this presentation right now is interacting with a silicone in the last 24 hours. One great example of this is in silicone adjuvants. So what I show here on this leaf is the same quantity of purple food coloring. The one that's spread out has a bit of silicone in it, while the one that doesn't has capillary action and is bound on the leaf. And so where the silicone and where this finds application is in herbicides. And so you can imagine that you want to add the silicone to your herbicide to spread it out more over the leaf, and then you use less of it in an agricultural application. How this material is made is shown with the chemical reaction in the middle of the slide. You take an alkene and add across it a silicon hydrogen bond, but what's required here is a platinum catalyst. And that's where the elemental footprint starts to suffer. Likewise, your kitchen spatula, as I showed you previously, or all the labels that you use in mailing applications have the same elemental footprint. So it's the same reaction where you take now a carbon-carbon double bond and add a silicon-hydrogen bond across it. And in this case, when you do it with two polymers, you make what's called a cross-linked silicone. That cross-linked silicone is the glue that you find on the back of a package label, for example. And this now becomes really consequential when you start to think about the catalyst that's used. So even though a small amount of platinum is required to promote the chemical reaction, you end up making a gelatinous material with very little platinum in it, that it makes it almost impossible to recover the precious metal. And so what that amounts to is around $300 million in lost platinum every year. So again, this concept of platinum is really hard to obtain out of the environment. You often have to dig over a kilometer into the earth and emit huge amounts of carbon dioxide to do that. We then concentrate the metal, use it in a catalytic application, never to be recovered again. And so the question we ask is, can we do better and use alternative elements on the periodic table to promote these reactions and perhaps even do better? And so the articulation of why these precious metals have an environmental footprint that they do is shown here. So you probably know that platinum is quite expensive. So it's around $6,000 per mole. What you may not know is it's what's called its global warming potential, which is the amount of carbon dioxide emitted to obtain 1 kilogram of the element in pure form. So you can see for platinum, this is quite high, 12,000 kilograms of carbon dioxide per kilogram of metal. For palladium, an element I'll tell you about in a slide or two, the numbers are equally as disturbing, meaning that you get almost 4,000 kilograms of carbon dioxide per kilogram of metal. If we go to now the first row of metals on the periodic table, cobalt and iron, what you can see, of course, is that the price drops dramatically, but also more importantly, from an environmental point of view, the carbon footprint does as well. So cobalt only has an 8 kilogram global warming potential, and iron all the way down to 1.5. So the motivation in my own research is to try to use cobalt and iron in place of these precious metals, platinum and palladium and rhodium. So one question you might ask is, why do chemists rely on precious metals in the first place? And the answer, of course, is they work. They work incredibly well in various catalytic applications. Why don't we use iron and cobalt? Well, where it comes down to is the redox chemistry associated with these two types of metals. Metals at the bottom of the periodic table, the ones that are terrestrially scarce on Earth, tend to redox cycle by 2 electrons. This is often why we make jewelry out of these elements, because they maintain their shine and their luster. When you go to the more Earth-abundant elements, you have to contend with more accessible 1-electron chemistry. And what that means is these elements tend to oxidize, or what you might know as rust. So a piece of iron, as illustrated with the nails shown there, turns that rust color over time. And so it's this fundamental difference in electronic structure between these elements that often dictates their function. And so the goal of our research is to try to figure out how to either take advantage of that 1-electron chemistry of the first row metal and do new catalysis, or to somehow transmute the function of iron or cobalt to act like rhodium, platinum, or palladium. And so in that silicones application, my laboratory a few years ago discovered these iron catalysts that would promote the synthesis of these carbon silicon bonds, the silicones. And what we found is that the iron catalysts are in fact more active and more selective than the commercial platinum catalysts. Unfortunately, as shown in the picture, the material labeled Karsted's catalyst is from platinum. The material labeled bisamino iron pyridine catalyst is from the one in the box. And you can see that the silicone has a little bit of discoloring to it in the iron case. That's not from the iron, it's in fact from the organic ligand that we use to support the catalyst. And so what we've done is we've used cobalt and nickel. And what these pictures show you, if you look carefully at the silicone produced, you can see how clear and colorless it gets as a function of the various catalysts we've made. And what that's an excellent illustration of is the catalyst loading. So you can see in the nickel case on the right, there's almost no detectable color in the silicone, and it's because the amount of nickel that's used to make the product is actually extremely low. And so now you can see a cost comparison, whereas the amount of platinum is around $1 or $3 per kilogram of product, the cobalt and the nickel are down to less than a dollar for sure. So you might not realize this, but the synthesis of medicines also relies on precious metals. And one reaction that's important is asymmetric hydrogenation. It's the way chemists introduce handedness into drug-like molecules. And a recent molecule that we've worked on is this one shown here in the box called Jagevapan. And it's a first treatment for migraine headaches that's intranasal. So you can inject this in your nose whenever you feel a headache coming on. And the part of the molecule illustrated in blue is the handed piece. And there's no precious metal known that will actually do the hydrogenation in a single step at low pressure to set that stereosensor and make the medicine. What we've discovered in our laboratory is that cobalt catalysts can do this. And so there's no rhodium equivalent of this exact reaction. And what we've shown is that the cobalt can now outcompete rhodium. It gives you quantitative yield, quantitative enantioselectivity, which means we only make one hand of the product and the reaction's complete in 15 minutes. So all of the features of this catalyst means that it's scalable and is certainly commercially viable because the cost is low and the performance is really excellent. A second transformation that's used to make drug molecules is what's known as cross-coupling catalysis. In this reaction, two pieces of a larger molecule are brought together to form, in this case, a carbon-carbon bond. So the molecule shown in the box is what's known as a TLR compound. And this one shown in particular is under investigation by Bristol Myers Squibb for the treatment of lupus. And as you can see, the synthesis of the core of this molecule requires two palladium catalyzed steps to form one bond. It's the bond shown in blue in the molecule in the box. So the carbon-carbon bond is made, and then the remaining carbon-carbon double bond in the six-membered ring has to be hydrogenated to give the desired final product. What my laboratory has discovered are these cobalt catalysts that are very straightforward to prepare and work on parts of the molecule directly that doesn't require two catalytic steps to form one bond. So the cobalt catalyst is able to make a carbon-carbon bond now that's more three-dimensional and directly deliver the core of the TLR antagonist. And shown on the right is the cobalt catalyst, which is this beautiful green color, and that's a 20-gram scale reaction being conducted at Bristol Myers Squibb. And this plot shows you how now chemists are looking more to cobalt than to rhodium. What it shows you is the number of publications for the two metals as a function of time in two different catalytic reactions, hydroboration and hydrogenation. And finally, what I'd like to talk to you about is the synthesis of sustainable aviation fuels. And as you probably know, aviation is one of the hardest industries to decarbonize. It emits about a gigaton of annual CO2 emissions, and this number is expected to increase dramatically by 2050 as emerging economies, especially in China and India, for example, become more wealthy and a rising middle class then desires to travel. And so electrifying or using hydrogen fuel cells in a long haul aircraft are pretty much untenable. So what we need are new fuels that are carbon neutral. And the area that we're interested in are cyclic alkanes. And as you see in the diagram on the right, sustainable aviation fuel could actually be quite attractive using these molecules. So what I mean by these are the molecules shown here. These are molecules in rings. And as you make the rings larger, it introduces strain. And when you burn them, you get energy release and hence excellent fuel properties. So the question becomes, can you make these molecules in a carbon neutral way? And so we've interfaced now with biocatalysis to do that. And so there's a method using enzymatic and whole cell chemistry to convert sorghum, which is a commodity glucose derivative, into isoprenolol and then ultimately into isoprene, which is the molecule shown on the far right. And the challenges with this is now converting that isoprene into a molecule that would be attractive for fuel purposes. And so what my group has done is developed iron catalysts that can do that and furnish these 8-membered rings selectively, which, as I'm going to show you, have very nice fuel properties. So to complete the reaction, a group at the University of California, Berkeley used platinum catalysis to do it. As you probably guessed by this point in the talk, we would prefer to use nickel catalysis. So we've demonstrated ways to do that. And most importantly, The fuel that we've developed, shown on the right, has superior properties to the jet fuel that was used to fly most of you to Shanghai to listen to this lecture. So what the point of this is that when you develop sustainable chemistry, there doesn't need to be a compromise. As I've shown you throughout, you can generate new fuels using iron catalysis, silicone products that have higher activity and higher selectivity, meaning less waste when they're produced. And in the example in the lower right portion of the slide, generate drug molecules directly in single-step reactions in other cases where you have to do multi-step and generate waste. Thank you for your attention.
That was another beautiful example of catalysis enabled by Earth-abundant elements. Okay, so next, let's join me in welcoming Professor Gang Chen, the Carl Richard Soderberg Professor of Power Engineering at MIT. So he will talk about photomolecular effects underpinning extra clouds absorptions and the superthermal solar interfacial evaporation.
Thank you, Peidong. Good afternoon. So I want to thank the WLA for bringing me here and listening to all those wonderful talks. And all those talks challenge the existing paradigm. And today, I will share another challenge. And this is what we call the photomolecular effect. I'll explain to you what we mean by the photomolecular effect. And I'm so happy to listen to Professor Zhair's talk on water, as I've studied his paper, but I was in mechanical engineering, we never met before, and also a lot of people working on atmospheric science. And I did not work on atmospheric science before. So let me start with what we know about water. Water does not absorb visible light. And in fact, at the peak of solar energy, water can propagate 40 meters. So we are all pleased to see clean water at the bottom of water. That's because water doesn't absorb. But then there is a big mystery in atmospheric science. And the experiment have measured that cloud absorbs solar radiation more than people could simulate. And those experiments, there are different types. There are cloud data. There are people flying airplanes to do measurement. There are also ocean data. And all this point to the extra absorption. But the theory couldn't calculate because the water doesn't absorb. And this is important because the absorption of sunlight really drives the Earth's atmospheric cycle, right? On the equator, it's warmer. On the poles, it's cooler. So all the air cycle is because of the absorption. And we didn't know this before, but I'll make the connection. And what really drove us to this is just a simple experiment that we want to do solar desalination. And we put black absorber parts on water surface to absorb sunlight and convert into heat, evaporate water. And we can easily calculate what's the thermodynamic limit, because thermal radiation, we know how much sunlight come in, and we know what's the latent heat, and then you calculate what's the maximum. And the maximum is about 1.5 kilogram per meter square per hour. So you can see my surprise, or my first reaction when I saw this paper published by Gui Huayu's group at UT in Austin, where they use hydrogel, polyvinyl alcohol, added with black absorber polypyrrole, and they reported the evaporation rate of over 3, twice the thermodynamic limit. My first reaction was, this is impossible. I brushed aside. And later on, I found there are more and more data report. People use different materials, different absorbers, different polymers, and even inorganic materials. And people even carbonize cow manure to do this. And so in 2019, I had a brave postdoc came in and I want to work on this. I said, why don't you try to repeat? And we also had a visiting student chemist. I was not a chemist, right? And say, okay, we have a team, so we spend a year repeating the data. And in fact, with the Professor Yu's help, we're able to repeat their data. And they had a theory, they say the latent heat of water in hydrogel is reduced. So we went to spend another 1.5 years to test their theory, including putting an electrical heater, because if latent heat is reduced, we can do electrical heating, we should say the same thing. And we didn't say it. At the same time, we had two new puzzles. One is that when we measure the absorption, you can see this is featureless. It's high absorptance because it's black, but doesn't depend on wavelengths. But when we use the LED to evaporate, you can see it peaks at the green. Green is water is least absorbing. And there's a factor of 2 difference between different wavelengths. That was puzzling. The second puzzle is when we measure the air temperature above the water surface, and this is done through a thin glass slide, so we can do thermal imaging. And what was surprising is that when we turn on the light, the air was actually cooler. And then when you turn it off, the air is hotter. And there's a very large region where temperature is flat. This is not a typical heating thermal behavior. So we're very happy to say this is a photon effect, with a suspecting photon effect. But I couldn't come up with a physical explanation. So we actually went back to test the thermal reduced latent heat hypothesis. We didn't show it. And then I had the time and looked into past literature and found all those reports. And this is when I asked, what's common among all this experiment? And it turns out the only thing I can find that's common is that surface area. All those materials has a lot of surface area, porous materials. So could this be an interface effect? Could actually light be absorbed by the interface? And I know one interface effect, we all know that. That's the photoelectric effect. A photon comes in, knock out the electron from metal. The question is, can a photon come in and knock out water molecules? And their problem, water doesn't absorb the green light. And second, water hydrogen bond energy is about 0.26 eV, and green light is 2.5 eV, 10 times difference. And again, I went to learn. I was working on semiconductor before, didn't work on water, and then learned that water is the most complicated liquid. And it's because of the hydrogen network, hydrogen bond network. But if there are hydrogen bonds, water clusters, then a photon can lock the many water molecular clusters, and it's actually easier to satisfy energy conservation. So, but we still need to come with a physical picture. What's the driving force? So here is what a hand-waving argument, why this could be possible. Here's a water-air interface with a hydrogen bond network inside. And Maxwell equation tells us across the interface, the displacement field is continuous. Displacement field is dielectric constant times the electric field, and dielectric constant differ by a factor of 2 at the visible light. So over the interface of 5 angstrom, there's a factor of 2 change in the electric field. Now if I look at a water molecule, hydrogen and oxygen atoms, and they are positive and negative charge, and they're not going to have a force balance, and that probably is the driving force. So it's a hand-waving argument, but that tells us I should see angle dependence, polarization dependence, if these effects are true. So when to check? First check is hydrogel might be actually absorbing, because it was clear, but with this realization, I told the other one, I said, why don't you go to dry the hydrogel and put a few drops of water so that there's still a lot of interface. And we go to measure absorption. Maybe there's absorption. And to our delight, yes. So this is a water, right? Absorption, this is the experimental uncertainty, basically 0 in the visible range. And this is as made hydrogel, this is powder. But when we drop a few drops of water, it starts to absorb strongly. We made absorbing material out of a non-absorbing material. And when you put a lot more water, the absorbance will drop. So we had a lot more experiment on hydrogel, but I don't have time to talk. But hydrogel is complicated. So I became more demanding. I said, can we look at a single air-water interface? Can we measure those effects? So we did a single air motor experiment. Here is a laser, a green laser, and then we have different polarization. And then we measure first the water surface temperature rise. We should not see any temperature rise because the water doesn't absorb. And then we do see it. Here's a normal incidence, doesn't have temperature rise. And then when light is at 45 degrees, it peaks. And only when the light has the electric field in the plane of incidence, this is the transverse magnetic field, you can see it's much stronger effect. And then we have thermocouple, we have infrared camera experiment. So this is a water surface. Let's look into the air side. Here is using a diode laser, and the idea is the diode laser will interact at the surface, excite the water molecular cluster, and that will change the refractive index of the air. And then I change the intensity, I will see the bending of the beam. And then we did this measurement. And again, in this case, this is a 520 nanometer diode laser, doesn't have response to TE light, and has a strong response to transverse magnetic field polarization. And it peaks at 45 degrees. And then with this, I can do different wavelength lasers. And here is the deflection, and you can see it peaks at green light. And then when we do the evaporation experiment from pure hydrogel as well as black hydrogel, it all peaks at green light. So they're consistent in this. And then when we heat up the water and then turn on the laser, we measure the air side temperature rise again. So green is a transverse electric field. Blue is there's no light. Between green and blue, there essentially not much difference. However, when we turn on the transverse magnetic field laser, again, we see this large flat temperature region. And then when we turn it off, that disappears. So why this happening? Here is our explanation. Light generates water molecular clusters, and they will break in air, and they will saturate the air, and once the air is saturated, temperature is flat. Can we see that from spectrum? So here is the infrared transmission spectrum. And when we turn on the laser, it's red. When we turn off the laser, this is black. You can see big difference between light on and off. And here is a single molar water vapor, single molecule IR spectrum. So there's a big difference. And we also did a Raman experiment. So this is a confocal Raman, and when we put a laser beam on the water surface, this is red, we measure water. And when we lift the water beam off the water, the laser beam off the water surface, we see a lot of features. And those features are very similar to water molecular clusters. Those blue are the people studying really water molecular clusters. So in this case, our explanation is the green laser excites the cluster and is probed by the Raman above. So we think we have really, in fact, now coming back to the cloud, does the cloud absorb? And here is a cloud experiment. We have a chamber, clear, no cloud. We generate water droplet, and then we shine LED of different wavelengths. And they should not heat up cloud. And then we do see the heating. You can see actually peaks at the green. So we over the years, we had done over 20 different experiments to check this hypothesis of photomolecular effect, and we think everything checked out. I'm not going to read through, but I do want to show one slide. I think this has a lot of implications. First, we think this is why this is happening to the bottle you're holding now, and this is happening to the clouds. This is happening on water, say, ocean surface. This is happening on soil surface. This might also happen in the plant transpiration. And how this will impact the weather and global warming models. Why does the photomolecular effect peak at green? We have no explanation. We have some hypotheses. We're working with people. And does this process happen in other liquids or even solid surface? How do we quantify this effect? How do we model this effect? And finally, my craziest question, which, again, I'm not a biologist, so why plants are green? Why plants reject green light? And coral reef is colorful. When plants migrate from ocean to land, they avoid the green light. Is there anything to do with this? So with that, I'm going to stop here, and I want to thank my group members and thank you and thank the scientific community.
Thank you, Professor Chen, for sharing the interesting insights on the photomolecular effect. Our next speaker is Professor Graham Farquhar. He's a recipient of a 2017 Kyoto Prize in Basic Science. He is a distinguished professor at the Australian National University, and his talk will be on optimizing water use by plants. Let's welcome.
Thanks very much, but I think that my title was a different one. Is it showing there? Thank you very much. Well, it's a pretty hard act to follow, learning about new properties of water that I had only recently heard about, and being challenged to explain why plants are green. I mean, normally we think plants are green because chlorophyll absorbs in the red and the blue, but maybe that's too simple. Okay. I felt challenged to think about what plant physiologists can do to contribute towards zero carbon emission. And so I took advantage of the current popular interest in artificial insemination, and I asked a popular, there's the biologist in me calling it artificial insemination. It's artificial intelligence, of course. And so I asked a popular AI program what it suggested, and I've got a few pages here. It was marvelous what it suggested. Carbon sequestration through plants, and there's a whole lot of detail about that. Enhancing plant carbon capture. bioenergy with carbon capture and storage, land use and urban planning, climate change and plant responses, so that includes impact on a range of spatial and temporal scales. And then, of course, like other scientists, we have a role in education and advocacy, policy recommendation, and so on. R&D is what we're hearing a lot about today, thanks to the organisers. And there's collaboration with other fields, and who knows, today may be a really good example of that. If it turns out that the properties of water that biologists had been missing turn out to be really important, then that, to my mind, will have made this conference worthwhile. Now, there are challenges and limitations that arise for a number of reasons, but I think plant physiology is playing a useful role, and it's likely to continue to do so. Having said that, I think the question arises about when somebody like a plant physiologist works on climate change issues, what sort of hat we should be wearing, and should people know what kind of a hat we're wearing. In other words, if we're convinced about the dangers of increased CO2 concentration, to what extent do we, when we talk, mix up our expertise on plant and their performance, and to what extent we let that expertise influence others to take action, which is sort of a political role. I say that because I experienced it firsthand a lot when I was involved in the Kyoto Protocol in Kyoto in 1997. And the question often came down to things that were not exactly science and not exactly politics, but sort of in between. And I guess I'd urge, my conclusion is that if we're acting as scientists, we have to be really clear about that and say when we're speaking as scientists and when we're speaking from our personal opinion about politics. But we've got to be careful not to confound the two. Now, vegetation, of course, is the biggest sink for atmospheric CO2. We're now talking non-artificial intelligence. We're talking about what I think. And the photosynthetic CO2 assimilation is going on now at a rate that's appropriate to the CO2 concentration of 2023. After some delay, tau, for example, we'll call it, the organic matter breaks down and returns the CO2 to the atmosphere. The average delay between fixation and decay might be, say, for example, 10 years, because you're averaging over things like forests, where it can be large, versus things like green algae in the ocean, where it can be very small. So the rate of sequestration of carbon, S for sequestration, is given by assimilation rate A minus respiration rate R, where R is the rate of CO2 released by respiration from plants and soil, and also decomposition of organic matter from plants. And so you can see that sequestration is the assimilation rate of this particular year, 2023, minus the assimilation rate of 2013, if tau is 10 years, for example. So sequestration is really the current gross primary productivity minus that which occurred tau years ago. So the models that try and include plants in the carbon cycle, and to a limited extent in the global circulation models, divide up the pixels into those having different values of assimilation rate or photosynthesis, and also those that have different time between fixation and decay. This can be handled in a more sophisticated manner, as you can imagine, so you can treat respiration as the convolution product of a respiratory impulse response function and a time-varying assimilation rate. And so the interesting thing about it, which most people don't seem to cotton on to, that if by some miracle the CO2 concentration were to become steady, then sequestration would be zero, and so we'd lose about 10 or 20 gigatons of carbon per year. And if the rate of change of CO2 concentration with time became negative by some miracle, the biosphere would become a source rather than a sink. Now, I thought I'd like to give some general comments about climate change that have impressed me. There's an excellent article by Palmer and Stephen, which I recommend, and it addresses the question about when we speak as scientists and when we speak as citizens and in between. I make the point that the greenhouse effect is a radiation imbalance, and of course the talk that we've just heard will complicate that the treatment of the radiation imbalance, I would have thought. Most of the extra long wave is balanced by greater long wave out. The long wave increase in from CO2 and other greenhouse gases, with a small increase in LE, which is the latent energy of evaporation. So you can see on the diagram there, on the left-hand side, we have the incoming. Is this working? I can't see the pointer. Oh, thanks very much. This is the incoming radiation, and you can see that that's a big effect. But the outgoing fluxes are mainly accounted for by the increase of temperature and the long wave radiation that causes. And so the change in latent heat and sensible heat at the surface is actually quite small. But that's not to say it's not important. So water is obviously an important limitation to agricultural production, but it's important in natural ecosystems as well. It causes a loss of productivity, but I emphasize from personal experience that we're all sharing this last couple of years that the lack of water is contributing greatly to increase in fire around the globe in all sorts of unexpected places and at unexpected times. So what do we think should happen to precipitation and evaporation? Well, we did a comparison of 30 runs from 20 different climate models and averaged things out. And you can see that for the globe, the increase in any increase in precipitation must be matched by the change in evaporation, and so the net effect is zero. For the land, the precipitation goes up by 41 millimetres a year, and the evaporation by 20, which means there's 21 in excess, which flows into the ocean. The thing that's puzzling to me is that means to get that water to run off in streams and rivers and creeks and so on, the soil must be slightly more moist on average, I would have thought. And so I would have expected that, at least in the first few years, the plant growth would increase. And that seems to be what we're observing. Plant physiologists and ecophysiologists and others working with remote sensing of CO2 are finding that plants are photosynthesizing now at a rate that hasn't been seen for hundreds of years, if not thousands of years. The increase in CO2 concentration and possibly an increase in availability of water is causing unprecedented growth. Now that sounds like it's a wonderful thing, and it can be in the right context, but a lot of it's going into rapid growth of grasses and is leading to increased inflammability, which we're seeing in Australia, Canada, United States, places, I understand in China as well, and in Europe. So that's just the behaviour at a global level. What about locally? It's thought that the Clausius-Clapeyron scaling, 7% increase in vapor pressure per degree, and it's thought that you could predict what would happen locally from that relationship. But it doesn't work. It doesn't work for the local level. The local level doesn't follow that prediction. So here were the predicted changes in precipitation, and you might see that Mexico was predicted to be very, very badly affected. I gave a talk at CIMMIT in Mexico, and after I showed this slide, the reporter rushed out and put it into the headlines of the local paper, which is a shame because the next slide shows about the observations. And the observations were that that part of Mexico was actually going to get wetter. Last point I'd like to make is that the climate has a chaotic nature. These eight pictures here of Australia were all done with the same model, given the same spin-up of history of CO2, volcanoes and whatever, and then allowed to have just the little bit of chaos that is noise in the atmospheric system. So they all started with just slightly different starting conditions, and that's the result of the decadal changes in precipitation from 8 different runs of the model, and you can see how dramatically different they are. When we got this result, some of us felt it might be too damaging to publish it, but I thought it was important. And the really good thing about it is that it shows you that when we take as reality the record of climate, of weather that we've seen, from national, international meteorological records, they are but one possibility for what the climate could have been. In other words, if somebody had jumped up and down in Brazil and a butterfly had flapped, the whole procession of results that occur after that could have been quite different. So the climate system is chaotic, and we've got to be careful about matching the existing climate and assuming that that's a given solid result. Thanks very much.
Thank you, Professor Facquel. Okay, so now we have our last speaker for this section, Professor Cheng Hong Zhang. She's a professor at the Department of Atmosphere and Oceanic Science, School of Physics in Peking University. She is also the director of the International Coordination Office of High Impact Weather Research Program. And she is also the Secretary General for Chinese Committee of the World Weather Research Program. Her speech is Early Warning for All, Current Understanding and the Challenges from Science. Let's welcome Professor Zhang.
Thank you, Chair, for your introduction. It's my great honor to be here to give a lecture. Okay, let's go. I think Professor Tianjun Zhou already told us our planet is experiencing a rising in the frequency and the intensity of extreme weather and climate events associated with the warming climate. So based on the IPCC AR6 report, the hot extremes has significantly intensified in most regions globally, and their rise is highly attributed by human activities, mainly in high latitude. And additionally, over 50% of the Earth's surface has observed a rise in heavy precipitation. And that does not mean we have plenty of water resource, because over 50, in the meanwhile, the agriculture and the ecology drought has also been detected on each continent, although their confidence level is moderate to low. And these countries bear a disproportionate burden in terms of mortality and the economic losses from these extreme weather and climate events. And the people in Africa, South Asia, South and Central America, and the small islands states are 15 times more likely to die from the climate disasters. And these disasters displace 3 times as many people as war. And the situation is getting worse. The high-impact weather events is mainly due to the extreme weather has been increasingly observed around the world. I have chosen the year of the 2021 as an example to show the location of those most severe cases. And we all know among them, the China's flood in Henan province has affected 14.5 million people and causing 398 deaths and more than 120 billion RMB economic losses. And the reconstruction after the disaster and will release huge amounts of carbon. And that is why we need an early warning system. As previous research showed, the earlier the warning, the less would be the loss. However, only 73 countries, as shown in blue color here, had early warning system until 2020. A third of people are not covered by the early warning, and only 40% have multi-hazard early warning system, according to the latest report on the state of climate service. So it was in the March of last year, the UN Secretary General announced a new action to ensure every person on Earth, no matter you are rich or poor, no matter you are in Shanghai or you are in Congo Basin in Africa, is protected by the early warning within 5 years, as humans are created equally. And in Chinese, we say 众生平等, and everyone has the right to be protected. And the EWS as the early warning system is an integrated system of hazard monitoring, the forecasting and prediction, disaster risk assessment, communication, and the preparedness activities, and the systems and process that enable individuals and communities, the government, the business, and others to reduce disaster risk in advance of hazard events. And that means every citizen on Earth is a part of the system. And the plot here, which is designed as a value chain by Brian Golden from Met Office, has summarized the process of warning system from science view. And we can see from the left, the observation, the weather forecast, and the hazard forecast, impact forecast, warning, and to individual decision. And we need scientists from sensor technology, atmospheric, and environmental, and social, and communication, and human behavior, and psychology to work together. And on the other hand, when the warning system is in operate, the flow of information is predominantly down the value here. So, and this needs to happen quickly and accurately and reliably to maintain the value of the information. And then nevertheless, the return flow information is still crucial, and because they're providing the update from the real situation so that the warning producer can maintain their situation awareness and be helpful for the model verification after disaster. As the system is complex, the challenges may come from each process, as showed in the green mountains here, and the gaps between the mountain is the bridge. And I'd like to choose atmospheric modeling as the example to show the challenge in process. As we all know, the atmospheric model is based on the laws of physics, showing in the equation here. And the equations are rewritten as partial different equations. And then the forecast of weather is an initial value problem. And given proper initial and boundary condition, the partial different equations are integrated. And then the model output will be analyzed by the weather forecaster or AI technology. And then we have the final weather warning production to deliver to the public. And the uncertainty may come from observations and analysis, imperfect physical process, computational error, and the limited sample from extreme weather and climate events, and the famous chaos. So if we want the early warning information may cover every citizen on Earth, and the kilometer scale model are required. And with the improved computation ability, of course, we can run our model in kilometer resolution. But however, there will be an increase in uncertainty as our observation system are not in the kilometer scale. And details of physics process, such as the deep convection behavior and the boundary layer clouds at the km scale remain largely unknown. Oh, sorry. And in the case of Henan flooding event, The CMA, they give a perfect, not the perfect, they accurately forecast of precipitation using their operational 3-kilometer model. However, the location and the intensity were incorrect. So the forecast will say there will be heavy precipitation in Jiaozuo city. But in the real case, the precipitation occurred in Zhengzhou city. Here. So there's a limitation of the model in predicting the convection, initiation, and the merging process. As a result, the predictability is quite low. If such an event were to occur again, I'm pretty sure it is unlikely we would be able to make a successful forecast. So despite the challenge from each process, the gaps between the different research area still exist in Henan flooding case. And we can see the weather and the hazard forecast are delivered to the public, but the impact forecast are not produced. The data is not shared between the Meteorology Bureau and the Ministry of Water Resources in China. And there are more than 8,000 rain gauge stations near Henan province, showing here. However, only the station in the upper panel was delivered to WMO and shared with the research communities. And I think this largely prevents the further relevant research. So enhancing the value of weather forecast poses a significant challenge. I think the heart of the challenge is the need for high-resolution observation. And the advent of smartphones has introduced a solution, probably, and with low carbon release might. Because just now I heard another professor, they say, I forgot how many how many carbon release for iPhone, right? But the smartphones are now equipped with sensors. And I put one here on here. This is the pressure sensor in your smartphone. And we can measure temperature and pressure and even aerosols. So if we motivate the citizens to participate in observations and the verification of weather forecast, hazard forecast, and impact forecast, and this could be an eco-friendly approach to obtain high-resolution data. And in recent years, I have collaborated with the Moji Weather company. Upon opening the Moji Weather app, the volunteers can collect pressure data and are encouraged to upload the pictures to the app, and which provide an important resource for model validation. And this app has the potential to transform the resource, to transform the value chain into a value network, and connecting scientists from different areas, and the governments, and the social media, and citizens for more effective disaster prevention in the future, I think. And here I show that in the 2018 year, the data is distributed on every continent in the world. You can see I put the number in the log 10. And you see except the Antarctica, and with very high density in the urban area. And we would like to see there's hot spots in the Shanghai and Beijing city, right? And I'm not sure how many people in this room has contributed with the hot spot. Can you raise your hand if you have the 墨迹天气 weather app? Okay, only a few. Thank you so much. And don't be worried. Some people just worry about their privacy, right? And I promise you, the label has been removed before we do research. And I think this app has also another interesting phenomena is the human behavior, because they tend to use the app when the extreme weather occurs. And here's, sorry. I don't know whether the movie, oh, it works. You see the gray, the ISO service of gray color is the 35 dBz in radar reflectivity, and the bar is the number of the people who use the app. And we can see when the hailstorm passes by, there's a jump of the people, a number in the request for the weather service. And after that, it goes down. And when the hailstorm moves to the Tianjin city, and there's another jump. So there is a huge demand for service during the extreme weather events. And therefore, we may have huge data during the extreme events, right? And currently, we have finished the data bias correction using AI technology. Since the time limitation, I'm not going to speak more detail here. And I just want to tell you the result. The initial bias is like minus 2.9 millibar, and the final result will be minus 0.19 millibar. So I think the result is very satisfying. And, oh, I have no time. So I have to go to my last slides. And finally, I think the purpose of science is to serve. And this is the distribution of people ask weather service every minute in China. I hope there's one day that all citizens on our planet own their own smartphone. And they can receive the early warning service, and they can also contribute one service observation for themselves and others. So I would like to encourage you to contribute a light to this planet. Please join our project to download the Moji weather app. But if you already have it, please open the app all the day and all night. And thank you so much.
Thank you, Professor Zhang. So with that, we conclude this part of keynote speech. And the next part is going to be panel discussion. I will pass this on to Professor Zhou.
Thanks to Peidong. Please welcome Professors Richard Zhe, Professor Graham Farquhar, Professor Peidong Yang, Professor Gang Chen, Professor Zhang Qinghong, and Liu Huai to move to the stage. Please. Thank you. In the keynote speech session, professors have discussed different topics of climate issues from different perspectives. Next, let's enter into the panel discussion. In the face of the urgent global warming challenges, science enables human beings to cope with current issues at such a strong and also unprecedented capability. However, we must act at a swift pace to fulfill a healthier, more adaptable, net zero carbon emission future under the guidance of science. And here, we have prepared a list of topics for you to freely share opinions and carry out discussions. The first question is to all panel guests. In order to mitigate the climate changes, we need to actively develop various zero carbon, emission reduction, pollutants reduction, and recycling technologies. The question is, what are some newly emerging methods or technology worth paying attention to in your focused area? Who is the early bird? Please.
This is. Can you hear me? Yeah. This is low technology, but there's been a great improvement in the speed with which people can revegetate. A lot of effort going on around the world in getting rapid planting of seedlings and choosing the right weather conditions to have them regenerate without dying. It used to be in the past that people gave them a lot of water and assumed that would see them through, but in fact there are better ways of doing it.
Thank you.
I think one obvious way to attempt to do this is to get away from putting out greenhouse gases. I think we understand that. And one interesting possibility that a number of us are interested in is, can we switch over from fossil fuels to using electricity that's not generated by fossil fuels? And there's much effort in different ways. To my surprise, I'm watching it, I didn't know it would happen this way. Wind has turned out to be quite important as a way to do this.
Okay. So I think for the CO2 problem, the one sort of big thing we need to decarbonize the chemical industry. So it's going to be sort of developing all these new process that's going to be replacing the existing chemical industry that utilize high temperature, high pressure, and also very energy intensive, carbon intensive. That basically, one example is producing hydrogen using solar, wind, or even including maybe nuclear, producing renewable hydrogen, and plug those renewable hydrogen into the existing chemical industry. That already will basically reduce significant part of the carbon footprint from the chemical industry. Then the chemical industry needed to think moving ahead to develop better catalyst, okay? All sorts of catalysts. We talk about, like Duxia talk about these room temperature nitrogen fixation. If that can be scaled up, that would be having huge impact on our society.
Thank you, Professor Gang Chen.
Yeah, I just want to give one example. This was the example that was mentioned. One could actually paint the roof to reflect sunlight, but also really to cool the room. And this is because there's a atmospheric transparency window, and if you design your paint correct, you can emit the radiation at room temperature to outer space at 3 Kelvin. And that's about 100 to 200 watt per meter square. And if you think about the solar energy, right, converting electricity, the efficiency at this stage is about 150 watt to 200 watt per meter square. So this could be actually a really cheap technology. My students are involved in some startups and developing those technology. But I want to make another point. This is for a lot of young researchers here. This is when you choose your research topic. And if you work, their fundamental science, like already talked, they say there was yesterday talking about the establishment of Princeton Advanced Institute study. So the usefulness of useless knowledge, right? There are fundamental science side that we need to continue doing. But if you work on applied side, and if you want to make a difference, then when you choose your research topic, ask the hard question: is your approach going to make a real difference? Can you solve a gigaton type of CO2 challenge with the approach you're taking? So that's just a call for the younger researcher in terms of your research direction and choosing your research topic.
Professor Huai Liu.
Yes, I think I can see a lot of young scholars here. So I'm thinking for the younger generation, actually we need to realize that on one hand we need clean energy, but another issue we are facing is the energy poverty issue. So that means for this generation, our duty is not only the clean energy, but at the same time we still need affordable energy. So we always need to keep that in mind. And also to cut the CO2 emissions, there are several sectors they were recognized as very challengeable or very difficult to abate sectors. So like those long-range transportation, the heavy trucks, aviation, and the shipping, and also like cement production as those. So those sectors are where we need more technology innovation, as well as sometimes we will need like mechanism design, so to accelerate the emission control.
Thank you. In addition to new energy, there are also some other matters in the climate adaptation, which is called climate intervention, such as the CDR technique. We can remove the carbon dioxide from the air. There are also some other matters. Any more comments?
Again, let me just give the example, right? The pen example. In fact, in a way, it's geoengineer because you're reflecting sunlight to back to the space, and at the same time, you can use radio cooling, right? So when you're actually doing that, you are, say, doing the, say, one stone, two birds type of action. I'm just giving one example. Of course, the CO2 sequestration is an approach that a lot of people are pursuing.
Yeah, this is a very important comment. In the past, we usually call this kind of matters as geoengineering. Now we prefer to use it as climate intervention. So there is difference in the technology. Thank you. Any further comments?
Yeah, just a very quick comment. CDR side, carbon removal and sequestration, or carbon removal and utilization. All of these sort of technology, if we are going to implement it, need to be implemented at a scale. Otherwise, they will not make a dent. So we're talking about gigatons. It's always, that's a scale we need to keep in mind.
And one more point. When we talk about this kind of technology, we still need to think about whether it would be an excuse for overshoot. So like, right now we want to cut our CO2 emission like this, but when they say, okay, we can wait, maybe we can overshoot and then cut more. So I think that's something we need to keep in mind.
This is also a new challenge to climate change. For the overshoot of greenhouse gas emissions, even when we recover the CO2 concentration to the history level, the climate cannot come back to the historical state. This is the new question. So let's move on to the second question. It's also to all panel guests. The breakthrough in net zero carbon technology requires comprehensive interdisciplinary cooperation. The problem cannot be solved alone by a single subject. The question is how to push the generation and the benign operation of the cooperation mechanism. Whether can it be fulfilled by establishing some major scientific plans such as the Human Genome Project in the field of biological science. So we need big project, international cooperation project in this regard. Any suggestions?
I wish I could be optimistic about that, but I mean the Human Genome Project was much more focused, whereas here we've got economics, population control. It's very broad. I think the IPCC has done a terrific job at pulling people together to write about the likely outcome of continued CO2 or greenhouse gas emissions. Maybe some of that experience could be used to focus, probably working group 3 or 4 or something, get them going within their own countries to represent some way to start this process that is obviously needed.
Thank you.
Yeah, so let me make a comment here. I totally agree, actually, the scope for this sort of combating climate change, the scope is very, very broad. We talk about science, technology, policy, social science, even going to the sort of changing the people's behavior. In that sort of broader scope, if you want to come up with sort of international, huge sort of project at international level, that's kind of difficult. But on the technology point of view, I think that's possible. So US actually did a small experiment, and many other countries are doing that, just for the science of technology, in order to sort of develop a new technology to do the CO2 capture and the conversion. That can be done. In the past, for example, the energy hub in the Department of Energy in US, it's a smaller scale, right? But if you really want to do this, you want to do the Manhattan sort of project scale, which is like several $1 billion over a couple of years. I think countries need to do that with much sort of better investment. Okay? So I think it's doable, but it depends on the different country need to really invest big. Because I think earlier, I think in yesterday's the keynote speaker mentioned that even as of today, many of the CO2 capture and conversion technology hasn't been used. And 50%, well, just using 50% of those technology. So lots of investment needed to be put on how to move sort of the next 50% onto the market at a scale.
Thank you. For such kind of international project, in the field of climate science, we already have some big project. In Professor Jiang Qinhong's talk and my talk, actually we have mentioned the so-called World Climate Research Program and the World Weather Research Program. They are big projects coordinated by World Meteorology Organization. And also under the umbrella of International Science Council, there is a big project called Future Earth. Future Earth tries to cope the problem of sustainable development by combining all the science from both natural science and also social science. Minutes ago, in the talk given by Graham Falker, you mentioned the work of Beyond Stephens. You know, Beyond and Tim Palmer, they are now pushing a very big project. It's called Earth Visualization Energy Project. The idea is to build a kilometer-scale modeling at a high computer, such as NVIDIA supercomputer, and then do kilometer-scale modeling. However, this kind of activity, is very, very expensive. So they're suggesting to operate this kind of international cooperation following the mechanism of CERN in Geneva. Each country can donate some fundings based on your GDP, and then we can share the resources. I know there are still some arguments from this. Anyway, this is a good idea from the scientist. This is the case for climate science. Are there any other suggestions for other subjects, such as chemistry, material science? If then there is no more comments on the second question, we can then move on.
Can I just put in a plea for broadening the thinking to include how we can reduce deforestation, because I think it was about 1930 when, only in about 1930 when fossil fuel emission first passed deforestation as the greatest source of atmospheric CO2. It's still an incredibly large flux. So anything that you guys can do to reduce the demand for farmland in Brazil and Indonesia and Australia, that would be a good thing.
Thank you. Let's move on to the third question. I think this question goes to Professor Richard Zerr and also Professor Pei-Dong Yang. It's on chemistry. You know, scientists used to propose that from the perspective of science, the currently available technical combinations is not capable enough to realize the goal of carbon reduction and also negative carbon emission. So strengthening or enhancing the cooperation of basic research is heavily needed, and a theoretical breakthrough should also be sought. This time, both of you and also other panel guests have a background in chemistry, which is also the most fundamental discipline with ability to promote interdisciplinary research. The question is, what are your opinions in this issue? Whether the chemistry can be the key subject to solve the problem in the carbon area? Does the subject of chemistry have the potential to push forward the development in this area? Please.
Yeah, that's a great question. I think earlier I mentioned the sort of decarbonize the chemical industry. I mean, chemical industry overall, it's all right now, if we look at the whole thing, it's all about small molecule activation. We'll talk about CO2 activation. We'll talk about water activation. We'll talk about nitrogen activation. The thing is, I do think we need a sort of technology and a scientific breakthrough that discover those new catalysts. Just like people did maybe 100 years ago when Haber-Bosch discovered that iron moly catalyst to fix nitrogen for the purpose of feeding the whole population, right? However, that nitrogen chemistry now is causing so much carbon footprint. Every 1 ton of ammonia you produce, you are releasing 2 tons of CO2. So now we need, I think, this generation of chemists, or in general scientists, or the next generation, the following generation of scientists, needed to quickly, we don't have much time, and you quickly come up with another new generation of catalyst that can run these chemistry. We cannot remove those chemistry. We have to activate nitrogen. We have to activate CO2. We have to activate the water. But chemistry itself, the catalyst itself, has to be replaced. And that's the scientific and the technology breakthrough we need. And we certainly, scientists need to be more creative. And we need to move the sort of speed of discovery in a much fast pace. And this is many of these sort of area we're talking about, artificial intelligence that can help us to discover new catalysts. And hopefully that will sort of revolutionize this catalyst development cycle?
I'd like to look at this question in a sort of a big picture view, if I might. And I'd like to start by going way back to a time when a man by the, I guess an economist, although not much people talked about economy then, Malthus. Malthus predicted that civilization was going to come to an end because we were all going to starve. He said the reason was that the rate of population growth was going somewhat exponentially, and the rate at which we could produce food was not doing that at all. It was much more geometrical, much flatter than that. And so he said, we'll starve. That's the Malthusian catastrophe. And, well, I don't think his calculation or his thinking was wrong, but in terms of what he was basing it on, but it overlooked the possibility that there could be a technological fix to the problem. And the technological fix, as Professor Pei-Dong Yang has said, came with the introduction through chemistry of fertilizers. Now, the reason why Fritz Haber made ammonia was not to feed the world. I'm sorry, that was not the beginning of it. It was really to make explosives. Okay, and this is important. This gets us to the question of dual use, but I don't want to go further with that. But I want to make sure you understand. We face, again, another catastrophe lurking, as very much you've pointed out. Okay, and it's true. And the solution, I think, must rely on some technological developments, breakthroughs. However, let me say to you that technology is not enough. I wish it were. Why I'm saying that is that you have to have society supporting the change. If you don't have that, it doesn't matter. And unless society wants to invest in the research, wants to invest in experiments that try to mitigate climate change, it won't happen, and we're in trouble. Okay, we're in trouble, particularly back to the analogy of what happens if you put a frog in a pot of water and you start raising the temperature. Okay, if the frog were to go into boiling water, it would jump out. Unfortunately, if you raise the water temperature slowly, the frog dies because it gets too hot. And we are in a similar problem that we have to recognize. And it's hard, particularly for politicians, to appreciate, I think, what I'm trying to say. And we all have to talk about this. And as a group, we will therefore influence people to change their thinking. And I think that's very important. So yes, technology, yes. Chemistry, certainly. Physics and engineering. I don't want to say chemistry is the only thing here. But much of that, it's very exciting. But we need also a change in the spirit of what people are seeking to do.
Thank you.
May I add a small point from my subject? You know, it's regarding the chemistry. I want to talk about the atmospheric chemistry. So why I want to add this point? Because we see in China, air pollution was alleviated a lot in the recent years. So actually we see when those trace gases components changed in the air, and the climate effects also changed. And recently, because of the global shipping changed the fuel to kind of low sulfur fuel, so the US NASA, they observed light scatter become less. So they call it climate penalty. So that means if we consider air pollution and the climate together, we will see we will need more efforts in future to alleviate global warming, because we need clean air. So we can't wait the air pollution, the sulfate, to cooling the air, but we want to remove those sulfate in the air. So this is also, I think, it's an aspect related to chemistry.
Thank you for your comments.
If I might add some more, something, at least at our particular session, we haven't talked about much, is, believe it or not, we all need greenhouse gases. if we had no greenhouse gases, we'd freeze. I mean it. Okay, you can do the calculation. So the question is keeping things in some right balance. Okay, and not discussed yet, I think, is the fact that to my way of thinking, the most important greenhouse gas is water vapor in terms of its effect. And no one is talking about removing water vapor because the Earth is 4/5 water. You know, we're not going to, okay? But we are other things we can control, and that's what we want to think about. And it's also not simply only carbon dioxide. Again, I want to get you to think about this, but there are things we can do, and we have to be able to measure to find out what we have as well. And there's much more effort that needs to be made that way. I was very interested in, I proposed the possibility of flying aircraft with something called a cavity ring down device that would allow you to look at the different gases in the atmosphere and make a map over the world. And I immediately got pushback from the military of various countries who said, you can't fly your plane over our space. You're spying on us.
So your comment on the greenhouse gases and the water vapor is very important. Maybe we have mentioned greenhouse gases too much. Everybody may think this is a bad word. Actually, without greenhouse gases and water vapor, our planet will be minus 18 degrees. In that regard, there will not be human being, there will not be culture. So the question here is, due to the industry revolution, the greenhouse gases had increased so fast. I think Professor Gang Chen also had comments on this. You talked about the water vapor.
Yeah, I think you're involved in ICPP document, and the water is not called a greenhouse gas because it's condensable. But its greenhouse potential is actually twice of CO2, if I remember correctly. So it's a very important. I just want to add that water is very important of the whole overall equation. And I do want to actually also come back to the idea of geoengineering, like already mentioned. Geoengineering has consequences, right? Let's say if we see the atmosphere by reflecting materials, like say some people say the dust, and we don't want the next, future generations to spend the time to clear that dust. So I think they say geoengineering by nature is actually really dangerous. But when I mentioned, like say the paint reflecting is actually, that's more manageable, right? It's actually doing the active cooling of the Earth and reflecting, but also reading out the radiation. So we've got to be very careful on this.
Thank you. The geoengineering is still at the research level. At the actional level, maybe the CCUS can be used in the practice. Yeah, please.
I just felt I had to make a stand for plant biology. The Green Revolution, for which the Nobel Prize was given, was for short stature wheat in Simit in Mexico and short stature rice in Erie in the Philippines. And it's true that these plants needed, were equipped to deal with more nitrogen, but it was a partnership between the harbour process and good plant breeding that gave rise to the Green Revolution. Thank you.
Thank you. Any other comments? I have one question to Professor Gang Chen. Your talk is quite new to us. Graham, myself, and Dr. Zhang Xinhong, actually we majored in weather or climate modeling. You know, there are large uncertainties in both the historical simulation and also the projection. Your process actually was never considered in our current model. So my question here is, do you have any plan to cooperate with meteorologists or climate scientists? Thank you.
That's what I found. This is exciting for me, right, coming here, because in fact, 2 weeks ago, I was looking at the American Geological Conference, and I thought I was 1 day late because I won't go there and tell people, I think there's this process happening and you don't know yet. I don't know. I need to convince people. I need more people to work on. But to me, coming here, all this panel, all you people here, and I was reading Professor Zara's papers on water, and because of the droplets, I was fascinated. I was trying to see whether there are connections. And then you talked about, say, plant biologists, trying to find the plant biologist to say, okay, is this too crazy to think about the evolutionary question, not the photosynthesis question, right? So I'm very excited. I'm a mechanical engineer, and I worked on water only last few years. And so I put this there, and I hope, I get people attention because this might happening. We have an experiment, we believe it happens, but you should question me, right? Because this is something, when I read the cloud paper, I have to say I'm an outsider, so I can be very critical. I thought the people, because they assume, when I saw the past analysis of the data, they actually assume that at the green light, there's no absorption because they fly. So they cherry pick, filter the other data. And to me, that was, why? I'm sorry, again, I'm very blunt. Why you guys do that, right? Of course, the data is very, when you fly 2 airplanes below and above clouds, I know that's very complicated. But we are, it seems to me, like making assumptions, of course, is based on existing knowledge. And I'm hoping this might provide say explanation, and I know this have a lot of controversy, and when I see this, I'm already expected to say I should be challenged.
Thank you, please.
A response to Professor Chen, I think his talk is very interesting because when we think about air pollution in China, we found actually when in those years the heavy pollution episode happens, usually the humidity is really high. So maybe not only in the cloud droplets, but also the water in the aerosol, they could have this kind of properties. So that's why maybe we see the light absorption or the other changes for the visibility. So very, and this is the point I would like to investigate more.
Wonderful. I want to collaborate with everybody.
Thank you. The time has gone fast. Let's move on to the fourth question. It's for Professor Liu Huan. The question is, how to more effectively push forward the cooperation between the science sector and the industry to absorb more social capitals, to focus more on the development of zero carbon emission reduction, pollutants discharge reduction, and also recycling technologies.
Thank you. First, I think for the scientists, we know like the topic for this forum, we agree that scientists are very, very important for climate mitigation. But for industry, I think they are critical to do the things because they are the major parties to do the innovation, to do the R&D, and to implement the new technologies. So how can scientists help? I think the first thing in my mind is we need like those big pictures. So this is like the top design. IPCC did a very good job. So right now, everyone agree with that we should cut CO2 emissions, but we need more detailed things. Like for every subsectors, so for those industries, they need to know what's their target. Because maybe not every subsector, they would think we should get carbon neutral in 2050. So maybe that's not their target, not the same. So we should help them to get the direction, and this would be helpful because currently the industry, they have that pathway dependency. So they really rely on the routine pathways. If they want to change, they need to have a lot of cost. So this is why we need to this top design. And on the other way is, I think the pathway design also very important. So here, I would suggest we can do like bottom-up research combined with top-down. So IPCC is doing a lot of top-down research, but when we see each subsectors, we see their parameters, their driving forces, they are different. So this is why we would need bottom-up things. And also for something else, like we could be the information bank, toolkit for industry to help them get the target, get the solutions. And one thing is maybe cross-sector. So I give an example for green hydrogen. This is the limited resource or energy in future. So we can use that to steel production to cut a lot of CO2 emission. And we can also use that to produce SAF or other alternative fuel for shipping, for aviation. So where should we use them? But maybe we can get those sectors, they cooperate together so they can have like a trade mechanism. But this is where the scientists and also the decision makers, they should work together. So finally, I would think maybe like cap and trade mechanism, which was used for environmental policies, would be useful again for the CO2 emission cut in the future.
Okay, thank you. The international project of Future Earth is also pushing the concept of co-design, co-production, and also co-delivery. Thank you. Next question goes to Professor Qinghong Zhang. You know, the frequency and the severity of extreme weather and climate events continue to increase. We have one question here is how predictable are these events? Moreover, how can we enhance the predictability to effectively prepare and also mitigate their negative impact?
Well, this is a very hard question because we have different kind of extreme weather. And I don't know about the how extreme, but I'm pretty sure maybe the deep convection, I mean the extreme precipitation, the probability will be decreased. You know, I know from the statistic, when the temperature increase 1 degree, the moisture in atmosphere will increase like 7%, right? And that means you have more moisture in the air, and it looks like we have more energy, and we have more gas in atmosphere, and you know, the convection, we don't know the CI process, I mean the convection initial process. So there's a lot of uncertainty on that. So I'm pretty sure of the extreme precipitation, the precipitation will be decreased. The second question, how to increase
the ability to cope with this kind of
I think the most important thing we need to do more observation, or do field campaign to make more very like high resolution observation, and then we can do more. We can add our knowledge to the very fine scale convection or something like that. But because I'm not studying hot stream or wildfire, I don't want to talk about them.
Okay, thank you. The time goes fast. Thank you all for the excellent sharing. Through the speeches from all the guests and also the discussion, we have gained deeper understanding about the energy transformation and the green development guided by the science. In our topic, in our discussion, we have covered lots of topics from climate policy to technology, from chemistry, chemical science to physical science. All these comments are helpful to the transformation of carbon neutrality. Thank you. Finally, let's have our photographer record this cherishable moment for everyone. Again, thank you again for your attendance, and hope we can meet up next year. Thank you. Thank you.